screen. Okay, so, um, okay, if you just thumbs up if you can see it because it doesn't show for me. Okay, perfect. For our next session, I'm going to be shifting roles from your moderator to presenting my own original frontline oncology research. Over the past several months, so obviously these 8 slides are not my entire work. It's just kind of an amalgamation of everything into something that I think I could deliver to you all now. So over the past several months, I have been investigating the complex metabolic microenvironments that malignant brain tumors construct to actively suppress the human immune system. So I am a year 11 student at Sharjah English School, UAE, and I am also the founder and president of the Global Youth Neuroscience Society, who is hosting the conference today. I am an aspiring neurosurgeon and a student researcher interested in neuro-oncology, neurodegenerative disease, and molecular neuroscience. My work has examined BDNF-mediated epigenetic alterations following early anesthetic exposure for pediatric patients undergoing surgery, circulate RNA regulation in Alzheimer's disease, and now I will be sharing my abstract on the metabolic drivers of immune suppression in glioblastoma. Just move this. Okay, so to begin, glioblastoma is the most aggressive brain tumor in adults. It accounts for around 50% of malignant brain tumors. And despite maximal standard treatment, median survival still remains approximately 12 to 15 months. And recurrence, which means the chance of it happening again, is almost universal. Even with surgery, radiotherapy, and chemotherapy, long-term control is rarely achieved. So this presentation, based on my research proposal, investigates why glioblastoma remains so resistant to treatment and whether part of this resistance is driven by active tumor responses to immune pressure. So why current treatments are not enough? Glioblastoma is a WHO grade 4 astrocytoma characterized by diffuse infiltration into surrounding brain tissue, which means it has tentacle-like the tendrils that go and invade the surrounding tissue, even though immune therapy is administered. Standard care includes maximal safe surgical resections where you remove the tumor, followed by radiotherapy and temozolomide chemotherapy. However, complete resection is not possible due to microscopic infiltration into functional brain regions. So there are some parts that it's just physically not possible to remove. In addition, glioblastoma shows high genetic heterogeneity, meaning that different tumor cell populations within the same tumor can respond differently to treatment. This combination leads to inevitable recurrence and progressive treatment resistance. So in principle, CD8 positive T cells should recognize and eliminate tumor cells. In glioblastoma, immune cells are often present within the tumor microenvironment, so it's a hot tumor, it's not a cold tumor, but they fail to control disease progression. This indicates that immune infiltration alone is not sufficient for tumor clearance. It raises a key question in the fact that is glioblastoma simply resistant to immune attack, or does it actively reshape or change the immune environment in response to it? So one key mechanism is IDO1, which is ideolamine 2, 3-deoxygenase 1. IDO1 breaks down tryptophan into kynurenine pathway metabolites, as you can see here by the arrows. Tryptophan is needed and it's essential for T cell activation and proliferation. So evidence shows that immune infiltration may be associated with increased IDO1 expression in glioblastoma because it's actively suppressing what we need to fight the glioblastoma. And this results in reduced tryptophan activity and accumulation of the metabolites that we don't want, which impair T cell function. Hold on. So the consequence of this pathway is essentially immune suppression. So tryptophan depletion limits T cell proliferation, and that reduces effector activity, so the T cells can't do their job. Kynurenine and downstream metabolites further promote immune tolerance and dysfunction. And as a result, T cells entering the tumor microenvironment become progressively less effective, even though there are high numbers of the cells itself. And this helps explain the disconnect that we see between immune infiltration and lack of tumor control in glioblastoma. So, IDO1 operates within a broader metabolic network. Other pathways involved include LDHA, which supports glycolytic metabolism, SLC7A11, which regulates redox balance, ARG1, which depletes arginine required for T cell activity, and TDO2, which also contributes to tryptophan metabolism. So, together, these form overlapping systems of immune suppression, and that redundancy is important because it shows us that blocking one pathway isn't going to be enough to restore immune function. Rather, we need to focus on all of them combined. Um, Current immunotherapy approaches mainly focus on enhancing T cell activation. However, these strategies may be limited if the tumor microenvironment actively suppresses immune function. And that suggests the need for combined strategies where immune activation is used alongside inhibition of tumor-mediated metabolic suppression. And in this context, IDO1 and related metabolic pathways represent potential therapeutic targets that could improve immunotherapy effectiveness in glioblastoma. So, just to conclude, glioblastoma isn't only just defined by its rapid growth, its aggressiveness, and its genetic heterogeneity, but it also is known for its active modulation of immune metabolism. So, why does the immune system not work here? And the central hypothesis of my research proposal is that immune infiltration may induce adaptive metabolic responses in glioblastoma, which reinforces immune suppression through pathways such as IDO1 and also all the other molecules I shared earlier. And understanding this relationship could help us explain why immunotherapy has largely failed in this disease and may point towards more effective combination approaches rather than just focusing on one single pathway. Finally, this work forms the basis of my current data-driven research project using R. So this is my abstract. However, using data analysis where you could analyze, I would be analyzing TCGA and IV gap data sets to test these relationships on a quantitative level. So we have actual numerical data. The abstract of the project summarizes this approach in a more structured computational framework. So we have definite proof, but obviously correlation does not always equal causation. So again, that there's a need for deeper investigation into such things. Thank you so much for listening, and I will stop sharing now.